our final speaker for this part of session 5 is Lucia Asencio Martin from Newcastle University, who will be talking about membership problems in automatic groups.
Thank you, Gemma. So the work I'm going to be talking about is a work in progress with John, Andrew, and Sarah, who are in Newcastle, and Dominic, who is in Madrid now and used to be in Newcastle. And the structure of the talk is going to be the following. I'm going to have a first part with lots of introductory definitions, like finite state automata, regular languages, etc. Then I'm going to give you an overview of a work by Karlampovich, Miasnikov, and Weil, where they proposed a solution to the subgroup membership problem in automatic groups. And then I'm going to be dedicating the last part of the talk to talk about a proposal of generalization for this previous work, so that it works not only with subgroups, but also with submonoids and rational subsets. And so if at some point you stop being able to see what my camera or something, let me know, because it's a bit difficult to frame.
Lucia, sorry to interrupt,
yes.
but is there any chance you can zoom in just a little bit more? It's just the text is a little bit small.
Okay, sure. Maybe I will have to be moving then, but okay. The whole sheet will not fit, but I will try to make sure that you see everything. Thank you, Gemma.
Okay, great. No
Is it
worries.
more or less readable this way?
Yeah, it's readable. It was just a little bit small, but that's a bit better already. So thanks.
Okay, thank you. So to start with, during this talk, I'm going to be referring to S as a finite involutive alphabet, and with involutive, I just mean that there is some kind of formal inverses inside the alphabet. Then S star I'm going to use to denote the set of finite words over S. And when I say language, I'm just going to mean any subset of the set of words S star. And in this talk, finite state automata are going to be important, so I'm going to define them. A finite state automaton is a finite directed graph that has some decorations, and the decorations are edges that are labeled by the elements in the alphabet S, a distinguished vertex that we call the start vertex, and we denote with this little incoming arrow, and a set of accepting vertices that are denoted with this double circle. An example of such finite state automaton would be this one, that has one start vertex, two accepting vertices, and then two other non-special vertices, and has labeled edges between these vertices. Is it more or less seeable, Gemma?
Yeah, I think we're good now. Someone's just quickly put on the chat. Yeah, I think we can zoom it in on our side, so I think you're good.
Okay, sorry, thank you.
That's right.
So, given a finite state automaton, we say that a word in S star is accepted by the automaton if the word labels a path that goes from the start vertex to any of the accepting vertices. In this case, A, B, C inverse would be an example. And related to this, and every finite state automaton has an associated language accepted by it. We denote it by the L of A, and it's just given by all of the words accepted by the automaton. This automaton on the example accepts the words A, B, and C inverse, AAC, AC inverse, AB, BC inverse, etc. And an example of a word not in this language is the word AC. So the family of languages accepted by finite state automaton is called the regular languages, and they are very well behaved. And yeah, that's why we like them a lot. And this finishes the first part of the definitions. The second part of the definitions is the following. So we're going to be using the notation of pi. We're going to be calling pi the projection of the words of we're a generating set into a group generated by that set, and an automatic group is going to be a finally generated group that is equipped with two things. On the one hand, an automatic group needs to have what we call a rational structure, which is a regular language L that projects onto the group. And the second thing that a group needs to have to be an automatic group is to have a set of multiplier finite state automata. These are finite state automata that are indexed by the elements in the generating set, and we're not going to need an exact definition for them, but just by their name, you can guess that they have something to do with multiplication in the group. And there are big families of groups, such as hyperbolic groups or ranks, that are automatic. And a typical non-example of an automatic group is a bounce-like solitaire group. So now that we know for what automatic groups are, going a bit away of them, we're going to be working with rational subsets of groups, which are just images of regular languages inside the group. So if we get a group generated by S and a regular language inside S star, the projection in the group of that such regular language is what we call a rational subset. And not just for rational subsets, but actually for any subset, in a group, we can define the membership problem. So we say that the membership problem for a subset of a group is decidable if, when we're given a word over the generators, we can tell whether the word represents an element in the subset or not. And given any subset of a group and given any language inside over the generators, but in practice it is going to be applying to the rational structure, so it's not going to be any language. The set of L representatives of such subset is the set of words in L that project onto X. So yeah, definition is just L intersection preimage of X. And putting these definitions together, for now on, the whole of the talk is going to be automatic, and I'm going to use the letter L to denote its rational structure, and M sub S for its multiplier. So in case I forget, remember L is just the rational structure of an automatic group. And putting all of these definitions together, something that is going to be very useful for the rest of the talk is to know that if we have an automatic group and any subset of the automatic group, the decidability of the membership problem for that subset is equivalent to the decidability of the membership problem for the L representatives of the subset. And this is, maybe like this. This is good for us because membership of X involves understanding the whole of the preimage of X, but the L representatives are a smaller subset that are potentially better behaved, much better behaved. So this proposition is going to be used throughout the whole talk. So give me a second to change. Now we're going into the second part of the talk. Let's see. Yes, like this. So the second part of the talk involves understanding in high level a work by Karl Lampovich, Viansnikov, and Weil in 2017, where they developed a framework to solve the subgroup membership problem in automatic groups. And this framework is made out of 4 ingredients that I'm going to be explaining to you in a second. So the first ingredient is to have some kind of initial finite state automaton that we call A0, and that reads the subgroup H. If we're given a subgroup, finally generated subgroup of an automatic group, and we have a set of generators for it, we can build an finite state automaton that we call A0, that is a rows type of automaton, which has one accepting and start state, and then one petal labeling each of the generators of the subgroup. And the special property that this has is that well, that we care about is that its language projects onto the subgroup. The second ingredient in what Karl Lampovich, Miasdikov, and Weil developed is a way of fattening this initial automaton A0. So this would be the equivalent of Stahling's foldings in a free group. And what fattening A0 meant for them is to be able to iteratively enlarge the automaton A0 to A1, A2, etc., to obtain a sequence of automata such that each of them accept more and more L representatives of the subgroup, such that the language of each automaton was contained in the language of the next automaton, and such that at every step, all of them projected onto H. Once we have this iterative process, the third ingredient that we need is a condition that ensures a geometric condition on the subgroup that ensures that if H satisfies that condition, there is an iteration of this process that I've called I0, such that the language of the automaton on that stage already contains all of the L representatives of the subgroup H. And this is important because of the proposition that I said in the last slide regarding the membership problem of H. And once we have these three things, we had an iterative process and a condition under which the iterative process works. The fourth ingredient that we have is that we need to build a test such that given a finite state automaton A, we can tell if the automaton already contains all of the L representatives of H, because it would allow us to stop this process from going forever. And this framework is like all of these things is what this paper from 2017 fills in. And I'm going to give some small details on some of these stages. So to start with, the fattening process involves two things. It involves getting an automaton AI and gluing relations to it, gluing relations according to the presentation of the group that we have. And with gluing relations, I just mean that for me, A sub I is a graph. And if it's a graph, it has vertices, and I can glue more vertices and more edges in. And we glue more vertices and edges according to some rules given by the presentation. And the second operation that the fattening involves is some edge identification, which is exactly the same as the one that we get for Stahling's foldings for free groups. So just identifying edges with the same label when they have the same origin. And this defines the iterative process, and the condition under which this iterative process ever comes to an end is if H is L quasi-convex. So L quasi-convexity was introduced in the 90s, I believe, and a subgroup is L quasi-convex. Remember that L is the rational structure of the automatic group G. H is L quasi-convex if there is a global constant K such that all of the L representatives of H are K close to the subgroup H. So in the Cayley graph of G with respect to S, this looks like the following. If we have any W, which is an L representative of H, and we draw the path starting at the identity, what we need to have is that each of the vertices of W are at distance less than K from an element in H. And if we have this, then there is iteration I0 such that the language at that iteration already contains all of the L representatives of H. And the test that they built for this uses the multiplied automata of the automatic group. So until this point, the automatic structure is not fully used because the multiplied automata are not used, but the automata are used in this point. I'm not gonna give more details about it. But in summary, what this gives is a way of building a finite state automaton accepting the L representatives of a subgroup when the subgroup is L quasi-convex and the group is automatic. And in particular, because of what I said, that this solves the membership problem of this subset, which in the case of an automatic group is the same as solving the membership problem of the subgroup. So yeah, in particular, the membership problem is decidable for L quasi-convex subgroups of automatic groups. And what we want to do is to have a similar framework, but that works also for submonoids or for rational subsets and not just for subgroups. So we need to fill in these 4 bits. We need to find some initial object, describe some fattening process, and then find conditions under which this works. And as a spoiler, we have this framework. We have a framework that works for submonoids, but this last part, we cannot do it for rational subsets, so we don't know how to find a test that detects the iteration I0 and at which we need to stop. Give me another second to change the slide. Something like this doesn't fit well. I hope I will move it when it comes. Okay, so last part of the talk is talking about the generalization of the framework that I've just described to you, but see if we can make it work for submonoids or for rational subsets. And the starting point is submonoids. So first we need to decide what the initial object is, and this is very easy because it's very similar to the subgroup case. So if we have a finally generated submonoid, we have a finite set of generators for it. We can build a finite state automaton A0 that is also a flower automaton, so has one start and accepting state and then petals. And the only difference with the previous one is that before we had an automaton where each petal could be traversed in both directions, but because of being a monoid, these ones we can only traverse in one direction. And once we have this initial object A sub 0, we can describe the fattening process, which in this case is more involved because it has to account for the fact that monoids are not closed under taking inverses. So in this case, what we need to do is do relations to each of the AIs, and this is the same as we had to do before. We also need to modify the AIs to accept words up to free reduction. This is some technical thing that happened for free when we were working with subgroups, but now we need to enforce it. And in this case, instead of the classical Stallings foldings, we need to do determinization of the finite state automaton, which is, if you don't know what determinization is, it's just a standard operation on finite state automata. So these 3 things together allow us to define the iterative process. And now what we need to give is a condition so that this iterative process comes to an end, so that there is an iteration at which the automata that we've built already, the automaton that we've built already reads all that we need to read. And in this case, because of submonoids having less structure than a subgroup, it is expected that this condition will need to be stronger. And the condition that the if and only if condition that the submonoid needs to satisfy so that this process comes to an end is what we've called L quasi-convexly undistorted. And we say that a submonoid is L quasi-convexly undistorted if there is a constant K such that for all L representatives of the submonoid M, there are some elements in the monoid that satisfy the following 3 conditions. The first 2 conditions are the same as in the case of the subgroup. So we need one element in the monoid for each vertex in the path described by this L representative W. And we need that each element of the submonoid is at distance less than k to the corresponding vertex in W. And we also need that I'm going to show you a drawing in a second, and you're going to see that, yeah, it is easier than it looks. The last of these elements is the same as the last vertex in W. So up to this point, this is the exact definition that we had before. And what comes new, so what makes it stronger, is that now for the process to work, we need to require that each mi plus 1 is in the mi times m coset of the submonoid. So in a picture, what's happening is the following. We need to require that for every L representative of M, if we draw a path representing that word W, each vertex of the path is a distance less than k from an element in the monoid. But additionally, we need to require that M2 is M2 is in M1 times M, M3 is in M2 times M, etc. And luckily for the case of a submonoid, the same test that worked before works now, so we don't need to do anything. And the reason the test works is because the test for subgroups is based in closure under product under multiplication, and the closure under multiplication is still holds for a submonoid. So now we go to the rational subset case. Remember that a rational subset is just the projection on the group of a regular language. And so if we take a rational subset, it's given by a regular language, and a regular language is by definition a language that is read by a finite state automaton. So RA0 in this case will be one of such finite state automata. It doesn't need to be a flower anymore. It can have several accept states. There's no relation between the accept states and the start states, so just a general automaton. And for the rational subset case, the fattening process is exactly the same as the one for submonoids. So nothing needs to be explained here. We're going to be doing the same as we did before. And the difference here, as before, is the condition that we need to impose on the rational subset so that the iterative process comes to an end. So the condition under which there is an iteration such that the automaton in that iteration already reads all of the L representatives of K is also L quasi-convexity and extortion, this time with respect to Q. So this with respect to Q is important and was not there for subgroups and submonoids. Remember, Q is the regular language that we've chosen to describe the rational subset K. And the definition is the following. For each, again, it's going to be a bit stronger than the previous one because rational subsets have less structures than submonoids. So we say that a rational subset K is L quasi-convexly and distorted with respect to Q if there are two global constants, so this C is new. There are two global constants such that every L representative of K, of the rational subset, has an associated W prime in Q and an associated F pairing the path defined by W to the point defined by W prime, such that the following drawing is true. So for each W, which is an L representative of K, I've drawn that above. There is a W prime in Q representing the same element as W, and each vertex of W is K close to an element of W prime. This element that is paired to each element of W, to each vertex of W, is defined by F. So W1 is paired with W prime of F of 1. W2 is paired with W prime of f of 2. So this is where this f plays a part. And the new thing here is that we're not only bounding this by k, but we also need to bound how far away these paired vertices are in the path W prime. So the constant C is bounding how far apart these W prime of f of I and W prime of f of I plus 1 can be. And if you are more familiar with this, what I'm saying here is that for each L representative W of K, there is a W prime in Q such that W and W prime asynchronously fellow travel with a linear bound, which is given by C. And as I spoiled before, the previous test doesn't work here because we don't have closure under multiplication. And for the last year, we've tried in several different ways to generalize the test that works for subgroups so that it works here, playing with some fake closure under multiplication that rational subsets have, but we've not managed to do this so far. So yeah, to wrap up, what we have is that for monoids, we have a procedure that builds a finite state automaton accepting the L representatives of a submonoid, if the submonoid is L quasi-convexly undistorted inside an automatic group. And in particular, since this solves the membership problem for the L representatives of M, it also solves the membership problem for the L representatives of, for the actual submonoid M. And for the case of rational subsets, oh, I forgot to tell you something. So in all the three cases, I'm stuck. The iteration I0 that we need to stop at can be calculated if we know the constants of convexity. So K in the first two cases and K and C in the last case. So actually a test exists if we are granted that we know K and C. And what we struggle with is building a test that doesn't use them. And the other thing that I forgot to say is that I don't know if this definition of convexity sounded very artificial to you, but it is not. And in particular, if we restrict this definition to subgroups or to submonoids, we end up with the exact same definitions that we had before. So this is just a generalization. And yes, so to finish off, if for a rational subset, we know that a finite state automaton solving the membership problem for K exists if we know that the rational subset is L quasi-convexly undistorted, but we only know how to build such finite state automaton if we are given the constants of convexity and the language Q. Okay, and yeah, so I am not sure anymore if there's a way of building a test that works well in this setting, so that works for all quasi-convex rational subsets of an automatic group. So we are trying to focus on some smaller places. So what happens if we assume that the group is cat zero as well, because there are other families of groups where other notions of Stallings foldings are defined, and maybe that could help us adapt the test to our case. So that's all. Thank you very much.
Thanks very much, Lucia. Let's thank our speaker. Do we have any quick questions?
Yeah.
Lucia. Sorry, Jacob, go for it.
Yeah, I would have a question. On the last page, you said that you only know how to build this finite state automaton if you know the quasi-convexity constant.
Yes.
And is that the case? Because if you know the quasi-convexity constant, can you bound the number of times you apply these folds during
Yes,
the
yes,
process?
exactly. So,
Mhm.
exactly. So I know that I have to repeat my iterative process up to a finite number of times, and that finite number of times, which I called I0, you can calculate by looking at the Cayley graph and calculating things in terms of K and C.
And what was C then?
What was, sorry?
K was the quasi-convexity constant, but C was what
Oh,
constant?
sorry.
What was C?
So for the quasi-convex notion that you need to work with rational subsets depends on two constants. It depends on it. You need to have for each L representative another word. And for this word, you need to know that each vertex in W is a distance less than K from a vertex in the other letter, in the other word, sorry. But you also need to know that these pieces here that happen in between, like these three pieces, all of them have less than C edges inside them. So that's the C.
Okay, I missed that. Yeah.
So yeah, you can compute in terms of these two numbers what the iteration I0 needs to be.
There's a couple of questions. Lucia, are you able to see the comments at the minute or the
Oh,
chat?
give me a second.
If
I'm not
not, I
going
could
to
read them
share
out.
this. Okay, please, yeah, because I'm
Yeah.
a bit unknown for
No,
this.
no, no,
Thank
you're
you.
fine. Don't worry. So this question from Corin Tan, does your argument for finitely generated submonoids also work for rational submonoid, i.e. rational subsets where they only accept vertex as the start vertex?
Oh, I don't know. I didn't really know what was that rational submonoid is, but it looks like it could be a bit better, so maybe I will look into that. Thank you.
Cool. I'm sure Corin Tan would be happy to chat at some point with you, Lucia. And then finally, Davide has asked, very naive, could any of this technology be applicable to asynchronous automatic groups?
Mm, I don't think immediately, but I've never really worked with asynchronous automatic groups, so yeah, I don't know much more than the definition, so maybe it is, and I could not see how.
Okay, great. So I'm conscious of the time, so let's thanks Lucia again.